Hello and welcome once again. In this video we will see how to make a custom inverse kinematic so that we can use it in Unity 3. If you have a Unity Pro, this video won't be any use of you since you can enable the IK with just 2 lines, but this is only for pro users. So now, what is inverse kinematics? Inverse kinematics is important to game programming and 3D animation, where it is used to connect game characters physically to the world, such as having our feet landing firmly on top of our terrain, putting our hands to touch an object. An animated figure, as you know, is modeled with a skeleton of rigid segments connected with joints. This is called a kinematic chain. The kinematic equations of the figure define the relationship between the joint angles of the figure and its pose or configuration. The forward kinematic animation problem uses the kinematics equations to determine the pose given the joint angles. Now, the inverse kinematic problems computes the joint angles for a desired pose of the figure. So now that we sounded smart reading Wikipedia, let's go and see what we can use in our game. I'm using the same project from the third-person shooter, since we will use it to fix the position of the left arm. So we don't have to put our animation inside Blender, change it, add new keyframes and stuff like that. So we can see how we can fix this without going into an external program, because we might don't know how to animate or how to create or how to fix a problem. So anyway, in order to start, now this we will have a lot of math, so if it's too much for you, just write along. And the good thing with this script is that you can reuse it for every project you want. So create a new script and open it up. But before until monodeveloper loads, let's talk about how we can do this. Now we will add some empty game objects as childs of our third-person character. We will call this elbow target or elbow, and we will call this IK. Now the elbow is where we want our elbow to look at. Now I'm going to go inside my own character, and since I want the left hand to be at the same place or near the gun, to have the correct position near the gun, I will put my IK target as a child game object of the weapon. So if we are shooting and place an animation that it shoots the gun, the IK target will move also and will move our left hand. And I'm just gonna call this hand placement. Now we don't care right now about correct positions. We will take care of this in the next video, where we're gonna fix some things to our third-person shooter project. So now that we have our targets, let's go to our open script. Let me zoom in. Now, the first thing we will need is our bones, the bones we want to use. Now, the bones we want is of course the upper arm, the forearm, and our hand. In a later video we will see how we can automate this stuff, so we don't have to drag and drop our bones from the hierarchy, from the inspector. Now we will need targets. The first target will be the hand placement, where we want our hand to eventually land, and the second will be the elbow, where we want our elbow to look at. Of course we want to add a bool if we have it, to say if we have it enabled, to open and close it, and we will add a float which we will call weight, so we have a smooth transition between opening it and closing. Now we will add some internal variables, and we will say quaternion. First thing we will need is a quaternion to save our upper arm starting rotation, our forearm start rotation, and the start rotation of our hand. So let's go add this. And one other thing, instead of writing this 3 times, if you simply do this, it's the same like writing this, but I'm just writing it like this, so it's more easier to understand. Now we will need to save our starting positions, meaning the position our targets have, our target and our elbow target have at the beginning of every frame. We will call the first vector 3 our target relative start position, and the second it will say our elbow target relative start position. And now we will need some helper game objects. We are using, because we will use, if we take every frame these transforms, we don't know exactly the orientation we will always be having, so we will create some helper game objects that we will make them look and have the position we want them to have, and then break our rig apart, put the bones to the positions we want them to look to the correct positions, and recreate the whole rig once again. So we will add our game objects here. We will call this, the first one, upper arm axis correction, The second will be forearm axis correction, and the last one will be hand axis correction. And now we need 3 more vector 3s, so we can store the last positions of each of each game object, so we can recalculate positions only if they are needed. The first one, we will call it last upper arm position. The second one will be our last target position, and the last one will be our last elbow target position. So that's it for our variables. Let's go to start. So let's start by assigning our start positions. So our upper arm start rotation is our upper arm dot rotation. Our forearm start rotation will be our forearm dot rotation, and our hand start rotation will be our hand dot rotation. Now we want to assign the relative starting position to our elbow target. So we will say our elbow target relative start position is equals our elbow target dot position minus the upper arm dot position. And now we want to create the helper game objects, so we don't have to do them inside Unity. And the way we do this is upper arm axis correction equals new game object, and we'll give it a name. We'll call it upper arm axis correction. Forearm axis correction equals new game object, forearm axis correction, and hand axis correction equals new game object, hand axis correction. Now we want to fix the hierarchy of the new game objects we created, and of course we will make the first helper game object our upper arm, and we will parent it inside our transform. Now for the forearm, we will parent it inside beneath our upper arm axis correction transform, and the hand will go, of course, under our forearm correction transform. So now let's go to update. we will not use update for now. We will use late update because we want the animation to already be playing, and then at the end of the frame to fix the position of our rig. And we will simply say if is not enabled, if is enabled. Where is it? Then calculate. Okay. Now as you see here, this will give an error, of course, because we don't have created the calculate AK function. So nice way mono developer have, if you go here, instead of going here and write void calculate AK, and however we do it regularly, you can simply select this, click refractor and create method. Now with the arrow keys you can simply see where you can place it. Now of course we will place it to the bottom. This is just a little tip. We delete this. So anyway, the first thing we want to do is, if we do not have a target, we want to reset the relative position. And we will say, of course, if target equals null, our target relative start position equals vector3.0, and we don't want to continue, so we'll add a return here. Now if we have a target and the relative start position is 0, then the target relative start position is our target's position minus our upper arm dot position. So we will say if target relative start position equals vector3.0 and our target is not equals null, then our target relative start position equals our target position dot position minus our upper arm dot position. Now we want to save our positions. We start with our last upper arm position. We will say we want him to keep the upper arm position. We want him to keep our target position, and of course we want him to keep the last position of our airball target. Now we want to calculate the AK angle, which defines the angle that will be subtracted from the upper arm axis, so it has the correct position. And in order to do that, we will need a float that is the upper arm, the length of our upper arm, which we will call upper arm length, and that is calculated with a vector3 distance, and we say upper arm position, forearm dot position. So the way we calculate the length of the upper arm is from the zeroed position of our upper arm the position it has until the position the forearm starts. Now we want the length of our forearm. And of course we find this by calculating the position the forearm starts until the position the hand starts. So now that we have the length of the upper arm and the forearm, we want to find the whole length of the arm, and of course this is done by adding our two values. And since we have the length of the upper arm, the length of our forearm, and the whole length, we can now find we now have a triangle, and by this we find the hypotenusa, how you call it. It's if you Google hypotenusa in trigonometrically, you understand what this is, if you don't know already. So in this case, a hypotenuse is our upper arm length, and now we need to find the distance between our upper arm and our target. And of course this is done by vector 3 dot distance upper arm dot position target dot position. Now of course, because we don't want him to, if the target is far away, we don't want him to stretch and break the joint and break a rig, so it's more realistic. We don't want him the target distance to be further away than the arm of the length. And the way we do this, we will say, we will manipulate our target distance, and we will say him to return using the mathf.minimum our target distance, target distance, our target distance and our arm length minus, we'll give him 0.0001f. Okay, this is this mathf will return the minimum between our target distance and the length of our arm minus a slight offset. So now we need to find the adjacent side, how do you call it? And this is adjacent, yes. Now the adjacent is the adjacent is the side of a pair of angles formed on the same side of a straight line when intersected by another line. Now I'll be happy to explain it to you in my own language, but I'm not even gonna try explaining it in English, so let's just move on. You can Google, this is pure math anyway, so you probably have done it already in school. So our float adjacent is our hypotenuse multiplied by itself, minus our forearm length multiplied by itself, and adding our target distance multiplied by itself, and all this we subdivide it by 2 multiplied by our target distance. Now this is how we find the adjacent in math. Okay, so now that we have all this, we need to find our IK angle. And we do this using the ICOS. mathf.acos returns the arccosine of f minus the angle in radians whose cosine is f. And we do this by adjacent subdivided by our hypotenuse, and all this is multiplied our math f rad 2 degrees. So this will take our adjacent and our hypotenuse and find us our IK angle. As I said, we have a lot of math here. So now, before we start making our IK, we want to save our positions, and we will say vector3 target position equals target dot position, and vector3 elbow target position equals elbow target dot position. Now we want to store the parent of each bone. We want to store NR scale of each bone. We store this so we don't have abnormal behaviors. You understand this, okay? Because we're breaking the rig apart and we are reconstructing it, these values might change. A lot of stuff can go wrong, so that we play it safe, we store all these values, and after we recreate a rig, we do a check on the values and make sure everything is as it's supposed to be. So now we want to save our local positions. Lots of variables in this one. And I missed something here. And of course we want to save our rotations. And we want to save the local rotation of our hand. So not only we will place it to the correct position, we want to make our hand have the same orientation as our hand placement game object, so we can have more control about how we want our hand to be. So here we just, of course, we save our parent transforms. We save our starting positions, the positions we have for our target and our elbow target. We save the parents of our bones. We save the scale. We save the position, the local position, and we save the rotation. So now we want to reset the arm to the starting. We want to set everything, so the IK will start from a known position and not to the last place it was previously. So target dot position equals our target relative start position plus R per arm dot position, our elbow target dot position equals elbow target relative start position plus upper arm dot position, our upper arm dot rotation equals our upper arm start rotation, our forearm dot rotation equals forearm start rotation, hand dot rotation equals our hand start rotation. So now we want to work with our temporary game objects and align them to the correct positions and then parent them to the arm. So our transform dot position equals our upper arm dot position. We position the elbow using as an up axis vector from the upper arm position to the target of the elbow. That will orient the elbow to the correct orientation. We want to the correct position we want him to look at. And we will do this transform dot look at target position and our elbow target position minus our transform dot position. Now let's do our upper arm axis correction. Dot transform dot position is equals our upper arm dot position, our upper arm axis correction dot transform dot look at forearm dot position, upper arm dot up and upper arm dot parent equals upper arm axis correction dot transfer. So for the first part, we place it to the correct position we want him to have, and place the upper arm axis correction. Maybe here we place the upper arm correction to the position we want him to have, and to the position we want him to look at the position we want him to look. So let's do the same for our forearm. And for axis correction transform dot look at forearm dot position, and the axis we want him to look at is the upper arm dot up the forearm dot up, and our parent we want him to be our forearm axis correction dot transfer. Okay, so as I said before, break the rig apart, we place it to the positions we want them to have, and we parent them to our helper game objects, and when we end with this, we'll recreate our rig once again. Now we want to fix our hand. Now we want to reset our targets, and we will say our target dot position equals our target position, and our elbow target dot position equals our elbow target position. So now we want to apply the rotation for our temporary game objects. And the way we do this is our upper arm axis correction dot transfer dot look at target elbow target dot position minus our upper arm axis correction dot transfer dot position. And then our upper arm axis correction dot transform dot local rotation equals our quaternion dot Euler upper arm axis correction dot transform dot local rotation dot Euler angles minus new factor 3 our AK angle 0 0, and this is where we start using our AK angle. So when we refix our rig, we want him to say have the position you had before, but have a slight offset to the position that will make you have the position we want towards our target. So now we want our forearm axis correction to transform to be look at our target, elbow target dot position is equals our upper arm axis correction dot transform dot position. Nope. Dot position. And finally we want a hand axis correction be transform dot rotation equals our target dot rotation. So now that we have all our axis set to the place we want using all this stuff here, we will now go and restore the limbs to the correct place. So we will say our upper arm dot parent, we want to be our upper arm parent, the stored parent we had. Our forearm dot parent will be our forearm parent. Hand dot parent will be our hand parent. Our upper arm dot local scale will be our upper arm scale. Our forearm dot local scale will be our forearm. Where is it? We missed something, I think. Let me go to our scale. Yeah, I wrote forearm here wrong where we save, so it wasn't auto finish it. So let's go fix that. So we restore our forearm scale. Next we want our hand to have our stored scale. Next, upper arm dot local position equals upper arm local position. Forearm dot local position equals forearm local position, and our hand dot local position equals our hand hand local position. So that's it about the places, the calculation of the IK. But now of course we have to do the transition, and we will say weight is mathf.clamp 01, and that will be our weight. Clamp 01 moves from 0 to the position you placed here. It's similar to a lerp, in some way anyway. So our upper arm dot rotation equals quaternion dot slurp upper arm rotation, and our upper arm dot rotation, and all this is based on the weight. And our forearm dot rotation is quaternion dot slurp forearm rotation, forearm dot rotation, and this of course is our weight. And our hand rotation, this doesn't need to have a linear interpolation, so we just hard code it and say hand rotation, we want it to be our target dot rotation. So this is it about our IK script. As you can see, this is a lot of stuff and a lot of math, and some stuff it's pretty difficult even for me, so don't worry, especially if I have to think of them in 2 languages. So don't worry if you don't get it, just make sure if you have make sure you don't have any errors. You have write it the same as I do here, but because there are it is a really difficult, you will find some links below to some other IK solutions. Some I will put all in the free. The paid ones, I think you already know which ones are, and you can use them if you have them. If not, you can use either this or any of the ones below. I researched some other ways and some of the free stuff that are available, and found some stuff. Some things are similar. Now there are other ways to make IK, there are other IK equations, but since this is enough for what we want to do here, and since we can use it, then there's no point to go with it anymore. So now that we have it, let's go back to Unity. So, and there is one error. Let's see where is the error. And the error is we cannot convert a vector 3 to transform. And the error is gone. Ignore the stuff. So now we have our RIK game object. We don't want this to be placed beneath our character or beneath this character, because we move the position a lot. So let's drop our script and let's start dropping our bones. We want our elbow target to be here. We want our target to be the hand placement, and we want the upper arm will be the left arm, the forearm will be the left forearm, and the hand will be the left hand. Now it will work even if you have just 3 game objects, even if you don't have a rig. So the way we do it is basically recreate the position we want it to have using dummy game objects, and once we have the correct positions, we just take each bone we put here to have the same position as our dummies. This is used a lot in a lot of games, in a lot of assets, almost everywhere. So now that we have this, of course we want it to be enabled, and if we hit play, as you can see here, we now have our array. If we take our hand placement, let's make it to global, and if we move it, we can move our array. Of course, this is a lot. We need to have a correct position for our elbow. And if we rotate our hand target, we can rotate our hand. Here I'm not rotating the hand of the bone, I'm rotating the IK target. So for now, this is about it for this video. In the next video we will see how we will implement this into our third-person shooter series, so we can fix the hand placement of the animation when we are aiming and when we are shooting, and we can see how we can change the positions according to what kind of weapon we are currently holding and stuff like this. We will also fix some other problems, some minor fixes to our existing third person, to what we have so far. I'm not making them inside this video because I'm guessing most of you won't look at an 1 hour video just for some fixes, so I will just make them there so you can find them and it's easier for other people to find. So this is about it. Don't forget to subscribe. Thank you for watching, and we will see you in the next time.